Let's talk about the units in the ring of formal power series over an integral domain R and the ring of Laurent polynomials over a ring R. Now recall that if R is an integral domain, then the units in R bracket X are exactly the same as units in R. That is, adjoining that new element X and making polynomials doesn't give us any more units. And recall a unit is an element that has a multiplicative inverse. So if we look at all the units in R, all the elements that have multiplicative inverses, that's all there is to the elements that have multiplicative inverses in R bracket X. We don't get any new invertible elements by adjoining X. But the situation is a little bit different in the ring of formal power series and the Laurent polynomial ring. So let's let R be an integral domain. The units in the ring of power series with coefficients in R are the set of all power series with constant term being a unit in R. All right, so we have a set equality here. The units in R double bracket X are the power series of this form. So let's prove one direction first. Let's suppose that we have a unit. Let me write A of X for the power series whose coefficients are A0, A1, A2, etc. So let's suppose that is a unit in R double bracket X. So that means it has a multiplicative inverse. Let's call that power series B. So it's a unit with multiplicative inverse B of X. B0 plus B1x plus B2x squared plus B3x cubed, etc. All right, well, if that's true, then A of X times B of X has to be equal to 1. That's what it means for B to be the multiplicative inverse of A. If we look at that closely, A0 plus A1x, etc., multiplied by B0 plus B1x, etc., equals to 1. So we have that product equals to 1. And that means that the constant term here times the constant term there equals this constant term. A0 times B0 equals 1. In other words, A0 has to be a unit in R, as does B0. So we just showed that if we have an invertible power series, that its constant term needs to be invertible in R. So that's one containment. The other containment is, let's suppose we have a power series whose constant term is invertible in R. And we have to show now that that power series is invertible in the ring of power series. So let's suppose A of x equals the sum of an x to the n, and a naught is a unit in R. So we've got to find a power series now, b naught plus b1x plus b2x squared plus b3x cubed, etc., that is the inverse of the A power series. So we'll write a naught plus a1x, etc., times b naught plus b1x, etc., equals 1. And 1 is 1 plus 0x plus 0x squared, etc. So we have this A power series. We're trying to find a B power series such that A power series times B power series equals 1. So I'll write that and try to solve for coefficients b0, b1, b2, b3, etc. If we can show that we can uniquely solve for these, then there's our inverse for A. Well, let's start with the constant term. So comparing constant terms, we have A naught, B naught equals 1. So constant term times constant term equals constant term of 1. A naught times B naught equals 1. Well, if A naught is invertible, then that means we can solve for B naught, that is. And we suppose that, where is it? Suppose that A of x equals this power series with A naught a unit. So A naught is invertible. So if A naught B naught equals 1, that tells us B naught equals A naught inverse. All right, so we just solved for the constant term of the B power series. Now let's look at the coefficient of x. Let's look at B1. So we still have this equation, A power series times B power series equals 1. That is 1 plus 0x plus 0x squared. So if we compare coefficients of x on both sides, we'll get something equals 0x. In particular, A naught times B1x plus A1 times B naught. That'll have an x also. Those are the two ways to get x. So comparing coefficients of x, we have, let's see, A naught B1 plus A1 B naught equals 0, because there was 0x on the right-hand side, and this is the coefficient of x on the left-hand side. Now let's see, there's 4 unknowns here. Well, I guess they're not 4 unknowns because the A series is given. A naught and A1 are given. And as a matter of fact, we just figured out what B naught is. So we have, in these 4 symbols, we have 3 of them are known and only 1 is unknown. B1 is the one that's unknown. So if we can solve for that, and I think we can, let's see. A naught B1 equals negative A1 B naught. But A naught, the constant term, is supposed to be invertible in R, so we can multiply by the inverse and get B1 equals negative A naught inverse A1 B naught. So I guess we just solve for B1. Now let's see if we can solve for B2. Comparing coefficients of x squared, we have, let's see, when we multiply the a and b power series, the x squared term is going to look like a naught b2 plus a1 b1 plus a2 b naught. Those are the three ways to get x squared out of the a series times the b series. So that sum of products has to be equal to 0, because on the right hand side of the equation here, the 1 equals 1 plus 0x plus 0x squared plus 0 every other power of x. So the coefficient of x squared on both sides is going to be this thing being equal to 0. All right, so there's 6 symbols there. We know the 3 a's because the a series is given, and we just solved for b0 and b1. Oh, so that only leaves b2. b2 is the only unknown here. So if we can solve for it, then we've got b2. So let's see. a0 b2 equals negative a1 b1 minus a2 b0. Just by subtracting. And then b2 is getting multiplied by a0, which is invertible. We assumed that. So if we just left multiply both sides by a0, we have b2 equals negative a0 a1 b1. Let's see, negative, let me write a0 times negative a1 b1 minus a2 b0. Oh, a0 inverse. So that's what that's what b2 ends up being. A0 inverse times this negative sum here. And it turns out every time we consider a new coefficient on both sides of the equation, we'll have one more unknown. And it's going to get multiplied by a0, and we can multiply by a0 inverse because it's invertible, and we can solve for that new coefficient. Let's see if we can write down this formula. More generally, we compare coefficients of x to the n on both sides. We just compared constant terms, coefficient of x squared on both sides. In general, we'll be comparing the coefficient of x to the n on both sides. To obtain, so we'll have a0 bn plus a1 bn minus 1, etc. up to a n b0 equal to 0. This is the coefficient of x to the n in the product, and the coefficient of x to the n on the right hand side, 0x to the n. So we have all of this. At this point, we will have solved for b0, b1, b2, all the way up to b to the n minus 1. So we can subtract all of this from both sides and put it on the right. And then we'll just have a0 bn on the left-hand side. So a0 bn equals negative a1 bn minus 1 minus minus an b0. So it's the same thing with everything pushed over to the right-hand side except for A naught Bn. A naught is invertible. So Bn equals A naught inverse times that sum minus A1 Bn minus 1 minus dot 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 An B naught. So Bn equals this. All of these have been solved already. So for every n, we're going to be able to solve for that coefficient in the B series, Bn. So since we can do that, then we have a recursive procedure to find all of the coefficients B naught, B1, B2, etc. All the coefficients of the B series. So this recursive procedure defines the power series B of x inverting A of x. Again, assuming A naught a unit in R. So therefore, all we need the power series AX to have is a constant term, which is a unit, and then we can invert it. So let's try an example. Of course, any example here is sort of infinitely long, but let's start doing an example. Let's invert 1 minus 5x plus 3x squared in the ring of power series with integer coefficients. So we're looking for 1 minus 5x plus 3x squared inverse. This is just a polynomial, but polynomials are special cases of power series. We just have all zeros after a certain point. So let's find the inverse of this in the power series ring. For this to be invertible in that power series, we just need the constant term to be a unit. Now there's only two units in the integers, 1 and -1. We've got a constant term of 1, that means that we can invert it. So we'll write 1 minus 5x plus 3x squared times b naught plus b1x plus b2x squared plus b3x cubed, etc. equals 1. The power series we're starting with times some unknown inverse equals 1. So we have 1 times b naught equals 1. So I guess b naught equals 1. We get that by looking at the constant terms of both sides. Now let's look at the coefficients of x. So let's see, that's 1 times b1 minus 5 times b naught equals 0. 1 times b1 minus 5 times b naught equals 0. We just said b naught was 1. So that's b1 minus, we just said, okay, b naught is 1. b1 minus 5 times 1 equals 0. So I guess b1 equals 5, because we have b1 minus 5 equals 0. So we just solve for b1. Then how about coefficients of x squared? So we have 1 times b2 minus 5 times b1, x and x gives us x squared, plus 3x squared b naught gives us another x squared. So 1 times b2 minus 5 times b1 plus 3 times b naught equals 0. B naught is just 1. Actually, b1 we know also. So the equation we have here is b2 minus 5b1 plus 3b0 equals 0. To shorten that, we've got b2 minus 5b1. b1 we said is 5, so minus 25 plus 3b0 plus 3b0 we said is 1 plus 3 equals 0. So b2 minus 25 plus 3 equals 0. So I guess b2 minus 22 equals 0. b2 equals 22. So now we know b2. Now let's look at coefficients of x cubed on both sides. So we get x cubed by taking 1 times x cubed, or x times x squared, or x squared times x. And normally I'd say or x cubed times constant, but we don't have any x cubed here. So there's 3 ways we can get x cubed. 1 times b3 minus 5 times b2 plus 3 times b1 equals 0. 1 times b3 minus 5 times b2 plus 3 times b1 equals 0. I guess that's a lot like the last equation we got here. 1 times b2 minus 5 times b1 plus 3 times b0. So the coefficients 1, negative 5, 3 are the same. I guess that really comes from the 1, negative 5, 3 here in the first polynomial. So let's see, we solved for b1 and b2 already. That means 1 times b3 equals 5b2, b2 is 22, plus 3b1, b1 is 5. b3 equals 5 times 22 plus 3 times 5, 55 plus 15, so I guess that's 70. I'm not sure we can easily see what an exact formula for Bn is, but we can see a recursive formula for it because we're going to get an equation for Bn in terms of the two previous B's. In general, it looks like we're going to get 1 times Bn minus 5 times Bn minus 1 plus 3 times Bn minus 2 equals 0. This will represent the 3 ways to get x to the n. We'll have constant times x to the n, x times x to the n minus 1, and x squared times x to the n minus 2. Those 3 ways to get xn, x to the n, are going to give us these 3 products of coefficients. So I guess in general, if we solve that for Bn, we've got Bn equals 5Bn minus 1 minus 3Bn minus 2. So this is a recursive formula for what Bn is. And again, it comes from looking at the coefficient of x to the n on both sides. Now in general, if we are inverting a polynomial in the ring of power series, we're going to get a recursive formula for the coefficients of the inverse. And if the polynomial has degree n, then let's see, degree n means that there's n plus 1 terms here. Then the recursive formula is sort of n long. Well, actually, if the polynomial has degree 2, there's 2 terms on the right-hand side. Maybe 3 total, including the one we're looking for. But we can get the one we're looking for in terms of 2 previous ones. So degree 2 polynomial means in order to recurrence here. In general, the inverse of a degree n polynomial leads to a recursive formula for the coefficients of the inverse, and it's recursive of order n. So in general, the inverse of a degree n polynomial leads to a recursive formula for coefficients of its inverse. And that recursive formula has the one coefficient we're looking at and then a linear combination of n more on the right-hand side. So if we have a power series R double bracket X have a lot more inverses than R does in R bracket X. So units of R are the units of R bracket X, but there's many more units of R double bracket X. Now let's look at Laurent polynomials. If R is an integral domain, then so is R bracket X inverse, as we showed before. And the units of the Laurent polynomials R bracket X inverse are just the units of R and well, we know one more unit. We know X is a unit because X times X inverse is 1. We introduced X inverse to make X a unit. So the units of R and all the monomials of the form U X to the n, where U is a unit of R. So if X is invertible with inverse X inverse, then X squared is invertible too. Its inverse is X inverse squared, which we could call X to the minus 2. And then X cubed is invertible, X fourth is invertible, X to the fifth is invertible. And each of those inverses is a power of X inverse. Then of course, if U is a unit, UX to the n is invertible also. And its inverse is just going to be U inverse X to the negative n. And to prove that, I will let you consider that on homework. And I will finish here. Thank you.